Okay, so this example, we are going to find the component form and magnitude of vector AB, and then we'll find a unit vector in the direction of AB. This time, though, our vector is in 3D space. We've already done this for a 2D vector, but now we're doing it for a 3D vector. And the process is pretty much the same. So let's get to it. In the last video, I graphed these 2 points in GeoGebra. Okay, vector A, or point A and point B, and then I graphed the vector that connected them from A to B, and then I showed you how to figure out the component form. Okay, so vector AB has this component form. The first is how far it's traveled in how far this vector travels in the x direction. Well, from -4 to 3, it travels 7, right? Because 3 minus -4 is 7. In the y direction, 6 minus -2 is 8. And in the z direction, -6 minus 1 is -7. So there's the component form of our vector AB. Okay. Let's now find the magnitude of AB. Okay, so in 2D, finding the magnitude of a vector is like using the Pythagorean theorem with the 2 components of your vector as the legs of your triangle, a squared plus b squared to get c squared. You take the square root to get your length of your vector. In 3 dimensions, it's pretty much the same thing. I just want to show you an illustration of why it's the same thing. Okay, so let's quickly come up with the formula for the magnitude of a 3D vector. Here I have drawn a box in 3D space. One corner of the box is at the origin of the x, y, and z axes, and the other corner of the box, the opposite corner of the box, is at a random point in space, okay, an arbitrary point, A, B, C. A is the x coordinate, okay, that's how far away that point is in the x direction, so I'll go ahead and label this edge of the box as A. In the y direction, it's gone B, and in the z direction, C. Okay, so A in the x direction, B in the y direction, and C in the z direction gets me to this point, A, B, C. Okay, now suppose we have a vector that is traveling from the origin to that point, A, B, C. So I'm going to draw this vector. Okay, so this orange vector, we'll call that vector V. That vector has the component form. Well, what's its component form? How far has it traveled in the x? How far has it traveled in the y? And how far has it traveled in the z? It has this component form, A, B, C. And I want to find the magnitude of vector v. So let's work on finding the magnitude of v. How long is vector v? Well, you may have done a problem like this in the past. In geometry, I give my students this problem where they have to find the length of this line segment that goes from one corner of a box to the other, but I give them actual values to use. Okay, and if you remember, the trick is to draw another diagonal inside this box, and this diagonal is across the base of the box. Okay, so from one corner of the base to the other corner of the base, that is one easy way to solve this problem. Okay, how do I find the length of that? Well, that is the hypotenuse of this right triangle that has A and B as its legs. Right? So if I wanted to find the length of this purple line segment, I would do A squared plus B squared, and I would take the square root of that. Right? So this purple line segment has the length, square root of A squared plus B squared. Okay, that's how long that one is. Now, you look, and I've actually created another right triangle that's inside this box. The base of that right triangle is this purple segment I made. The height of the right triangle is, I'll just draw another right angle here. The height of that right triangle is C, right, in the z direction, and the hypotenuse of that right triangle is our vector. So if we could find the length of this hypotenuse, that would be the magnitude of our vector. Okay, and we're going to do that the same way we did the last one. We're going to use the Pythagorean theorem: one leg squared plus the other leg squared, square root of that sum. Okay, so the magnitude of vector v equals the square root of this thing squared, square root of a squared plus b squared squared. That's one leg of that triangle, plus c squared. Okay, and you see the beautiful thing about this is we have a square root canceling with a square. Okay, so the magnitude of vector v is just the square root of a squared plus b squared plus c squared. So it's the same thing as with a two-dimensional vector. You just make sure to add in this third component, the z component, into your formula, and you've got it. So let's go back to our example, and let's calculate it. Okay. Let's find the magnitude of AB. We're going to get the square root of the x component squared plus the y component squared plus the z component squared. And we get the square root of 49 plus 64 plus 49. And what do we get for that? 49, 162. Okay. So there is the magnitude of our vector AB. And can we simplify that? That's a good question. 162, that turns out to be divisible by 81, which is a perfect square. So I could turn that into root 81 root 2, and so I get 9 root 2. This thing keeps getting out of focus. I'm sorry, guys. So there's the magnitude of our vector AB. That's a length of a vector in 3 dimensions. The last video you saw what that vector looked like. This is the length of that vector. Okay, so we've got the component form, check. We've got the magnitude, check. One other thing about magnitude, guys, is I know I gave you this formula, a squared plus b squared plus c squared, square root of that. You'll usually see it like this, a lot longer, x2 minus x1 squared plus y2 minus y1 squared plus, and the same thing for z, z2 minus z1 squared. Okay, this is when you don't already have the component form of your vector. Okay, this is for when you have the x, y, and z coordinates of the 2 points. Right, so if I wanted to, before I found this vector in component form, I could have used this formula to find the magnitude and just used -4 and 3 as my x values, -2 and 6 as my y values, and then 1 and -6 as my z values. Okay, so that's how you'll typically see that formula in your textbook and on Canvas and stuff like that. Okay. Anyway, we've got the magnitude. That's done. Now we need to find a unit vector in the direction of AB, and I'm going to focus this thing another time. Okay, so let's do that. Unit vector. So I'm going to give my unit vector a name U. Okay, and my vector U is in the same direction as the vector AB. So I'll just draw a picture just to help you guys think about this. Here's A, here's B, here's the vector AB. And we know that it has the length, or the magnitude, 9 root 2. And I want to make vector U in the same direction as AB, but only have a length of 1. Okay. Now, you might remember from the last section that to find the unit vector, we just need to take all 3 components of our given vector and scale them down by a ratio, and that ratio is the reciprocal of our magnitude, 9 root 2. Okay, so if I take 9 root 2, 1 over 9 root 2, and multiply that by each component of our vector AB, that will give me the components of our U vector. Okay, so it would be like taking all the components of our vector AB and dividing them by 9 root 2. That would give us our components for U. Okay, same thing with 2D, but this time in 3D. So the formula is just to take 1 over the magnitude of vector AB and times that by our vector AB. Okay, so let's do that. So that would be 1 over, and what's the magnitude of AB? That is 9 root 2. We just calculated that. Times the vector AB, 7. 8 and -7. Okay, so we're just going to distribute that scalar in. So we're going to get 7 over 9 root 2, 8 over 9 root 2, and -7 over 9 root 2. Okay, That is the unit vector. Now, of course, we have radicals in the denominators of our components, so we need to rationalize that, and we do that, of course, by multiplying the numerator and denominator by root 2. So our x component, we're going to get 7 root 2 over 9 times 2, 18. 8 root 2 over 18 again, and negative 7 root 2 over 18. And the only one of these that simplifies is this y component, because 8 and 18 have a common factor of 2. So 7 root 2 over 18. This would become 4 root 2 over 9. And negative 7 root 2 over 18. So this vector has a magnitude of 1, right? If we calculated the magnitude of this thing, it should give us 1. And you can check that if you want to. And it is in the direction, the same direction as our vector AB. Okay, so there we go. We just found the component form, we found the magnitude, and then we found the unit vector in the same direction as our vector AB. Okay, that's it for that one.